Hi, welcome to your third tutorial in the organic analysis series, and this one is on a process called infrared spectroscopy. So we're moving on from mass spectrometry for now to a different type of process that gives us slightly different information. So infrared is another analytical technique which gives us information about functional groups that are present within a compound. It doesn't give us any structural information and it's not actually used as often anymore in working labs. It's used in universities and colleges and things like that, but it's mostly been replaced by other processes such as NMR, which you'll come across next year, which is much more useful, but you still need to know about it for A-level and for university. So infrared spectroscopy works on the basis that if infrared radiation hits a covalent compound, hits a molecule, the bonds within that molecule absorb infrared radiation at characteristic wave numbers. So certain frequencies of infrared will be absorbed by different types of bonds in different compounds. And the bonds that are in those compounds will respond to this increase in energy by moving, by bending or stretching. So you can see some of the different types of stretching that you can get here. So we've got symmetric stretching where the hydrogens are moving away from the oxygen at the same time and then moving back again, or asymmetric stretching where one is stretching and the other's contracting and then they go the opposite way. And you can also get different types of bending, so where the hydrogens are coming together on this one and then moving apart. They can twist and wag and do all sorts of weird things with different names, but it's all as a result of being hit with this infrared radiation. So if we just have a little look at how it works with a sample and some infrared radiation. So here we've got a sample which we can put into our IR, and your infrared radiation hits the sample. This is a very simplified version. If you have a little look on kind of Google Images at how it works, it's a little bit more complicated, but essentially, because you don't really need to know it for A-level, infrared radiation hits a sample and some of the infrared radiation is transmitted out the other side and just goes straight through. Now if all of the infrared that went through that sample was transmitted, you'd get a transmittance of 100%. However, we know that if we've got some covalent compounds in there, that the covalent bonds in there will absorb some types of infrared radiation, so you also get some absorbances as well. So you end up with a transmittance of less than 100%. Now what the infrared spectroscopy does is it takes the information from what's been transmitted and what's been absorbed, and it particularly looks at the wave numbers that have been absorbed, and connected to a computer it produces a spectrum. So we're looking at another different type of spectrum like the one on the previous slide. So this is the sort of spectrum that you would get out at the end. So you can see up the side here we've got transmittance on the y-axis, which goes up to 100, and you see that the transmittance is not 100. All of the peaks are below 100. So we've got some hexanoic acid molecules and the bonds within that are absorbing some of that infrared radiation, so that the transmittance is always less than 100. Along the x-axis we've got this unit called wave numbers, and the units for wave numbers is centimetres to the -1. So it's the same as 1 over centimetres. So it's a bit like wavelength, it's the reciprocal of wavelength, the inverse of it. So if you've got a wave and its wavelength is 0.0005 centimetres, to convert that into wave numbers, you just do 1 over the wavelength. 1 over 0.0005, and your units would be in 1 over centimetres. So your answer would be 2000, and it would be centimetres to the -1, which is just another way of writing 1 over centimetres. So a wave of wavelength 0.0005 centimetres is going to come out somewhere around here at 2000 wave numbers on the spectrum. Now that's all for your information, so that you understand kind of what the axes are on this spectrum. You will not be asked about wave numbers or where they come from or what they mean. You'll just be expected to be able to state specific wave numbers where you get different functional group peaks. So don't worry about wave numbers or what they mean, that's just for your information. Now the rest of the spectrum is where you get all the interesting information. So we've got a series of peaks. I know they're very strange, they point down instead of up, but it's because they're absorbing, so they're taken away from your transmittance. These peaks are how we identify particular functional groups. So this broad peak here is going to be representing an OH bond, and the slightly narrower one in here, they're kind of overlapped, that's going to represent CH bonds. So you can spot that you've got OH bonds and CH bonds in this molecule. This peak here, very characteristic, very strong narrow peak here, is a carbonyl, a C double bond O stretch. And then we get kind of below 1500 and it all gets a little bit complicated. So when you're working with infrared spectroscopy in your exam, you need to consider it in kind of two parts. So we've got the stuff to the left of 1500 at higher wave numbers. This is where you look for your characteristic peaks, your OH bond and your C double bond O, your carbonyl. Everything below 1500, this is known as the fingerprint region. And you do need to know this. And it is between 500 and 1500 centimetres to -1 wave numbers. Okay, so that's there-ish. So when you're trying to identify something, you look for your characteristic peaks above 1500 wave numbers. But you might be asked, how would you look at infrared spectroscopy to confirm that this compound is hexanoic acid? So if you're asked about confirming that it is something that you thought it was, your answer is pretty much always you would check the fingerprint region. So this region here is a series of peaks that are unique to that compound, like a fingerprint. So you would check the fingerprint region, and then you also need to say, and you would compare it to known spectra. So you would get the spectra of all the things that you think it could be. So you know it's got an OH, you know it's got a C double bond O, start looking at carboxylic acids, get some of those out, maybe do some other chemical tests. But to confirm that the compound you've got is actually hexanoic acid, you would have to print off hexanoic acid's infrared spectrum, and then you'd have to get the one for your sample that you're testing and compare the fingerprint regions, or compare the whole thing directly. So 2 marks probably. Look at the fingerprint region and compare it with a known spectrum if you want to confirm that it is what you thought it was. Okay, so final little thing I wanted to say about the spectrum is just to be wary. Don't know if you can, it's quite small, but here you've got one scale, and over here your scale changes a little bit. So you're going from 1000 to 1500 there, and then 1500 to 2000, and then in the same sort of distance you're now going up to 3000, so your scale does change. And that does happen on infrared spectra because we're looking at particular areas, and it really doesn't matter that the scale changes. You just need to be aware so that when you're reading off where peaks are, look carefully at the numbers either side to identify what wave number this particular peak would be at. So look carefully at the scale either side of the peak that you're looking at. Okay, so we've got all of these characteristic peaks that appear at specific wave numbers, and you need to know what they represent. So very nicely, in your exam, you'll be given this little table that tells you it all. So infrared spectroscopy questions, I think, are really quite easy. So as long as you know your answer about the fingerprint region and checking it against other spectra, and you know to look for these wave numbers, you're probably going to do all right on these sort of questions. So if you get a peak between 300 and 3500, it might be an amine. Between these, characteristic of OH in an alcohol, be careful because you've got slightly different wave numbers, slightly lower wave numbers if it's in an acid. So you can consider whether it's an alcohol or a carboxylic acid, and then you've got all of these other ones as well. Now, obviously here we've got CO bond, here we've got CC bond. If you notice, they're quite low wave numbers. They actually appear over in the fingerprint region, and actually it's quite difficult to tell. So you're going to want to look for these sort of peaks. This one, maybe this one, that one, and your carbonyl is another very common one. So some of them you might not be able to see because they're in the fingerprint region, but they will give you this table. And pretty much all of the questions are, here are two compounds, here is a spectrum, which compound is this the spectrum for? It's a lot of comparison, and it's looking at peaks that should appear there. Are they there, or are they not there? And being able to figure out which molecule you're looking at. So I'll go through in a past exam question, a real one, to show you how simple it is, really. So we've got a spectrum. The infrared spectrum shown, what was below, I've put it above, is either that of butan-2-ol or of butanone. So we've got a secondary alcohol and we've got a ketone. Identify the compound to which this infrared spectrum refers, explain your answer, and you may find it helpful to refer to the table of infrared absorption data on the back of the periodic table. So you'll want to look at that. So looking at the infrared absorption data, if your compound was butan-2-ol, you would expect an alcohol OH stretch around 3230 to 3550, which is going to be here somewhere. So we do have a stretch in that area, but if it was an alcohol, it would tend to be quite a wide stretch, something like that. What we've actually got is a very pointy, narrow peak instead. Now, that pointy, narrow peak is actually representing CH bonds. So you'll come to recognise the some of the shapes. So if we've got an OH bond, tends to be quite broad at that particular wave number. A C double bond O tends to look something like that. And CH bonds are a bit kind of jaggedy, so you get something like that. So you'd be able to recognise whether you've got an OH or a CH, even though they appear in the same part of the spectrum over here. So it's looking at the moment like there is no, no OH stretch. So it's looking like it might be butanone. So the next thing to check is, does it have the characteristic stretch that you would expect in butanone? Butanone is a ketone, so it should have a carbonyl group, which is this one here. So 1680 to 1750, which is here. We have got a stretch, and it is that sort of shape that I've just explained to you there. Carbonyls, just a long, thin, pointy stretch. So it does have a C double bond O. Okay, so if this was a 4-mark answer, you've got 2 of the marks by pointing out the functional groups that are present or not present. So there's no OH stretch over here, and there is a characteristic carbonyl stretch here, so there's 2 marks. Your other 2 marks are for using the wave numbers in your answer. Okay, so no stretch at 3230 to 3550 wave numbers, but there is a stretch at 1700, so that would get you the 4 marks if you say what the wave numbers are and what the functional groups that they represent are. And you can see I've put in 2 different ways here, so no stretch at, and I've put a range of wave numbers, but when I can see a stretch, I've tried to pick out the wave number that it's at and gone roughly for 1700. So in the mark scheme for this, they probably allow somewhere between 1700 and 1710 for that peak. Now, I'm not going to go through any more exam questions because basically all of the exam questions are that sort of thing. So either one spectrum with a couple of possibilities, they might join it up with some information of reactions. So you might have an organic reaction going on, it'll tell you what the reactants are, and then the product produces a spectrum. So they might make it a bit more challenging that way. They could also do a multiple choice one, so for this compound, is it spectrum A, B, C or D, which obviously takes a little bit longer to have a little look at because they don't look very simple at first glance. You have to have a good look at these peaks and figure out what's where. But basically that's what you need to be able to do. Either identify which compound the spectrum is for, or identify which spectrum goes with a compound, or discuss this knowledge of the fingerprint region between 500 and 1500 wave numbers, and that is used to identify a compound, definitely. So it's a very quick tutorial. There really isn't a lot to it, but that is infrared spectroscopy pretty much. So if you would like to go and complete your post-tutorial quiz, make sure you do have your notes from this tutorial that you're going to bring with you to next lesson, so that you're able to access the questions a little bit easier.